Welcome everyone, Azure Cosmos DB Live TV. Welcome. I'm Mark Brown, your host. Episode 28, we're going to talk about a pretty cool new feature. I've been really excited to talk about this for a long time. And I'm joined today by Deborah. Hi, Deb. Welcome back.
Hey, Mark. Good to see you again.
Good to see you. And then I got new guest, Hierarchical. How are you, sir?
Hey, Mark. I'm doing good. How are you?
Good. Well, it's great to have you guys on, and I'm excited. Deb. This is going to be a great show. This is such a cool feature that I think customers are just going to love. Let's just get right to it, huh? Let's get cracking and talk about this, huh?
Yeah, I agree. Glad to hear you're excited about the feature, Mark. So we actually built this feature because we got a lot of feedback from our customers that there were certain very common scenarios that they were trying to partition for that they just couldn't come up with the optimal partition key. And when we dive into the scenarios, we see prior to the feature that we're working on called hierarchical partition keys, this was actually not possible to come up with the right partitioning strategy. So what we're going to do today is Mark figured to show you one of the common canonical customer scenarios of why this feature is so important and why it helps solve that problem. All right, so the customer scenario is a multi-tenant scenario. And let's say in this scenario that we can keep track of login information for a customer, but it really could be any kind of event information for a tenant. Now you have many different tenants. Some of them are very large, like a Microsoft tenant. Some of them are much smaller, and each tenant has between 1 to 100,000 users. Now, in terms of the data access patterns that we want to optimize for, remember, as a partitioning best practice, when you want to choose a key, you always want to think of how am I going to access my collection? What is my read and write pattern? So let's go through all of those and see, based on that, what kind of partition key we should come up with. So for our write operations, we obviously have some inserts. So for every event that happens, it'll get inserted into Cosmos DB. And then we also have read operations. So the read operations we want for our multi-tenant scenario is we want to be able to get all data for a single tenant. We want to get all data for a particular user in a tenant. So I might want to get all the data for Alice in the Contoso tenant. And then, of course, I also want to be able to read single event data for a single user in a tenant, maybe given by some time or some other filter. And this is what a sample document could look like. So we'll have some notion of event ID, some notion of a user ID, tenant ID, and the timestamp. So given all of this, what do you think a good partition key should be for this scenario?
It seems like everything is by tenant, so I'm going to say tenant ID. Would that be a good choice?
Tenant ID is definitely a great starting choice, and it actually will work for many scenarios, but there are a few key requirements that if you do have as a customer, that it actually will run into some trade-offs that you will not like and not have a good time with in the future. So let's actually go through and analyze how tenant ID does as a partition key, as well as some other options, and finally see how this new feature that we've been working on can help solve these problems. So the option one, as you mentioned, is tenant ID. Now, before I dive into the analysis of how the key does in the workload, I just want to quickly explain this diagram here. So this diagram here is in the context of a container or collection in Cosmos DB. And it's a model of what happens behind the scenes when you write data or try to read data from the system. So each purple box here is what we call a physical partition. It's a physical piece of hardware where your data is actually written and stored. Each blue box here is a logical partition, which is a grouping of all of your data, a logical grouping of all the data with the same partition key value. So what happens when you write data in Cosmos DB is you pick the partition key, and Cosmos DB hashes the value of that partition key. So for example, let's say you partition by tenant ID, and a new document comes in, it has tenant ID Contoso. So we take Contoso, parse it out, figure out a hash, what that hash is to, and then based on whatever that hash is to, we assign it to one of the physical partitions that we know it should go on. So each physical partition is assigned a range of potential hash values, and whatever you hash to, that's the physical partition that you end up staying in. So as you can see, because we do that hashing, all the data for a single logical partition will always be on the same physical partition here. So all my data for Contoso is in one logical and physical partition, Fabricam, and so on. All right, diagram makes sense?
Yep.
Cool. All right, so now let's take a look at how all of our data access patterns will work for this workload. So the first one we wanted to look at was querying by tenant. So like you said, Mark, a lot of our operations are be able to filter by tenant ID. So naturally, when we query by tenant, because we know the hash of the tenant ID value, we can efficiently go to a single physical partition and retrieve our data. So this query gets a check, very efficient. The next thing we wanted to look at was querying for a particular user in a tenant. Again, as long as we know the partition key and are able to provide it in the filter of our query, we're able to get that data in a single partition efficient query. So this is a check. Now, what happens though if some of my tenants get really, really large? For example, this Contoso tenant might become hundreds of GB, even terabytes, if we're lucky as a customer to get a really big tenant. So in Cosmos DB, each logical partition is constrained to 20 GB of data. So that means that once a single logical partition hits 20 GB of data, you actually cannot, you've filled up the partition, so you can't write any more data to it. So this solution really is not going to scale if you do have large tenants. Now, of course, if all of your tenants are relatively small, all under 20 GB, then tenant ID will work. But the moment you try to pass this threshold, it's not going to continue scaling there.
The guidance we've given, I think, historically has been to either do salting of the partition, so Contoso and Contoso 1, Contoso 2, or have them create what we call the synthetic key, right? Where we would say, okay, use your tenant ID and then find some other property that exists in there, and then just concatenate them together and make that your partition key, right?
Definitely. The synthetic key is definitely, I think, the most common workaround that we previously did suggest. So let's take a look at how well that does and see how it performs with the same workload requirements. So now let's take tenant ID and user ID. So the good thing here is you immediately see we've added more cardinality or granularity to our partition key. Before, tenant ID could just was only had one value for a tenant. Now, if I have 100 different users in my tenant, I now have effectively 100 different hash values that I could have. Now, the only problem here is when I query by a tenant, because the hash is actually the hash of the full value, the Cosmos DB system cannot parse out what the tenant is and route it to the right physical partition without having to visit all the partitions. So that means that anytime you query by a tenant, let's say I want to get all the data for the Contoso tenant, it's very probable, given this the way the hashing works, that it could be spread out among all your physical partitions. So if you've got 1 or 5 physical partitions, not a big deal. The typical RU overhead to check a physical partition is between 2 to 3 RUs, so not too bad. But the moment I start hitting, imagine 100 partitions, 1,000 partitions for those really large workloads, the overhead for those RUs is not going to scale and lead to a negative performance impact. So as our workload grows and we continue to scale, this query by tenant is going to get slower and slower and less efficient. Now, if we want to query for a user given a tenant, we're still in the clear here because we can provide the tenant and user ID. It can construct our partition key value in our query filter to provide both pieces of information. But unfortunately, in order to do all of that, our application and query complexity has increased a lot. When we write the data, this concatenation of tenant ID, user ID, probably doesn't exist organically in our data set. So we have to create a new property for it, like synthetic key or partition key, PK, whatever you want to call it. And when you want to query for a particular tenant, if you want to scope it to a single partition, you have to specify and construct all the different user IDs that you want. So it actually becomes a lot harder to maintain, but it does get you out of this 20 GB problem. Since you're unlikely to hit 20 GB for a single user in a tenant, you now have enough granularity to continue scaling beyond there. So we've definitely solved one problem, but as you can see, we've introduced a lot of trade-offs in other areas.
Yeah, it makes sense. So I guess then the solution then is that's going to be the hierarchical partitioning, right? We've got.
Yes, Mark, it's the rule of threes. Option 3 is always the best one. The best one. But even without that, if you look at this intuitively, it kind of seems like you want to be able to partition somehow by both of these keys, right? Like if you could just partition first by tenant ID and then by user ID as like a sub-partition, right? Then we could somehow get out of all of these problems. So this is exactly the scenario that are the new feature hierarchical partition keys, sometimes referred to as sub-partitioning, is designed to solve. With hierarchical partition keys, we now let you partition by up to 3 levels of keys, and typically they'll follow a hierarchy of what is natural in your data. So for example, in our scenario, we can partition first by tenant ID and then sub-partition as our next level by user ID. And because of the fundamental changes we've made to the way we do query routing, the hashing, as well as the split logic, we're now able to satisfy all of our data access patterns without any of the previous trade-offs.
Can I ask a question about is it too early? I wanted to ask, like, how does the consistent hashing work with this type of thing? Is there, you have a hash on the tenant, and then say you have a hash on the user. Are those combined in some way or not? Or is this just something else where it's just something completely different, I guess?
Yeah, that's a great question. Hierarchical, you want to take this one?
Sure. Yeah, so that's right, Mark. So we take the hash value of both the tenant and the user ID, then concatenate the hash values and use them as a hint there for the partition placement. So that way we are not losing out on the natural hierarchy that the documents or the dataset might have, and all the documents that have a single the same tenant value reside in the same physical partition. So
the routing is really truly a hierarchy in that there's when you have, say, a partition split, when for a user, it's going to obviously has to keep that same consistent hash for the tenant, and then I guess I'm getting myself confused a little bit.
No, yeah. So it's how you described it. It is hierarchical in a way. So first we look at the hash value for the tenant, and then we look at the hash value of the user ID, and we combine with both the combined value of both these hash values is used as a hint for the partition placement. So
the range then is not just a single or a range of the single value; it's a range of this hierarchy, if you will, right?
Yes. Now, yep. So exactly. So it is in a tree structure, right? So previously, imagine if the tenant had a range between 1 to 10, and user ID had a range between 1 to 1,000, right? So now each of these tenants now will have a single range of 1,000. So that way we are increasing the range for the entire data set.
I see. Okay. All right. I think I'm cool.
Yeah, it's pretty cool stuff. I'll show a picture too, so maybe that can help as well.
Yeah, pictures work for me.
But the good news about all of these updates that we made is that now we can satisfy all the data access patterns. So the way it works is you as a customer will tell us what the keys are, and you don't have to fuss around with creating any new synthetic properties in your document. In your documents, we'll know, okay, you've told us tenant ID is your first key, followed by user ID. And the way it works is that all the data with the same tenant ID is actually going to start on the same physical partition. And if a single partition ends up getting too big, exceeds the 50 GB physical partition limit in Cosmos DB, then we'll split the data. So roughly half the data for the tenant is in one partition and half in the other. So instead of before, where you would run into a 20 GB limit when you only partition by tenant ID, because you've given us the second key, you've kind of given us inbuilt more granularity. So we can take that hint and use that to further subdivide the data once you hit that limit. So once you, for example, if a physical partition starts to fill up, let's say this Northwind Traders tenant was getting really big, it had hundreds of thousands of users, it was filling up a single physical partition, we would then split that into roughly 2, where roughly half the data with half the users would be on one and roughly half would be on the other. And we're able to do that, unlike before, because before when you told us your partition key was only tenant ID, we didn't know what other property to use to distribute the data or to further subdivide. But now you've told us, you've given us the hint, and now we can use that to split like the second part of the range, as Hierarchical alluded to, and continue adding more physical partitions as needed so your data continues to scale.
Do you have any kind of heuristics for what data when you do a split goes into each in there? Are you trying to kind of be cute and predictive in terms of, okay, this is likely to split again, or that type of thing? You know what I'm saying? Like you want to minimize the amount of times you're moving data behind the scenes. I get it. So I don't. Is that too much secret sauce going on there, or is there something? Is there some logic behind that you can share?
Yes, Mark. Like we do optimize the split point detection in some way. So how we currently optimize it is like we try to move the entire data of a single tenant to be on a single physical partition. For example, let's say the split point for a partition N, as Deborah has shown in the picture, ends up to be falling somewhere in the northwind tenant. But the tenant northwind is, let's say, very small. Say it's only of size 5 MB. So we do not want to split the northwind tenant into two physical partitions, because whenever the user is running a query saying like where tenant ID equal to northwind, he has to hit two physical partitions. So instead, we try to move the data into a single physical partition. But in the case where the northwind is quite huge, the data set of the tenant northwind is large, we end up splitting the data into both the partitions. And today, the first split point that we pick is the median, and the later optimizations that we try to do move the split point from the median.
Do you look at something like request volume or anything so that you're kind of evenly keeping things kind of smooth, I guess, in that respect? Or
no, currently, like the optimizations that we do is only based on the size of the data that exists on the partition, not by the request.
Okay, so storage. Got it.
Yeah.
Okay.
Yeah, request volume is definitely an interesting one to think about in the future. Then, I think based on how your request volume goes, you could imagine in the future being able to know like if one partition, logical and physical partition, is really hot, maybe that's something that might need more throughput than others. But anyways, stay tuned. We can plenty of content for.
Yeah, that's cool.
I've already said too much. All right. So coming back to the topic of hierarchical partition keys. So like I mentioned, in this feature, you'll now be able to set up to 3 levels of keys. Think of these as your L1, L2, or L3 key. So your new effective logical partition is the concatenation of all 3 of these values. So for example, in our scenario, we did tenant ID and then user ID as the next level in the hierarchy. So the main benefit to you as a customer is in these scenarios, like these multi-tenant scenarios, you can now get the optimal partition strategy for these as your data size continues to grow. And now any logical partition prefix can exceed 20 GB and 10,000 RUs. So before, when you partition only by tenant ID, you run into 20 GB limit as soon as a logical partition hit 20 GB. With subpartitioning or hierarchical partition keys, we have the second level granularity, so we can keep letting you write that tenant exceed 20 GB, 100 GB, whatever amount of data, as long as the effective logical partition of tenant ID and user ID have enough cardinality to stay within 20 GB. And this also implies that data for a prefix of a logical partition can be on multiple physical partitions. So for example, like the example we just talked about with Northwind Traders, if Northwind Traders was really big, it was taking up the entire physical partition, getting very close to 50 GB. If we split that in 2, now roughly half the data for Northwind is on one partition, half the data is on the other physical partition. So if you continue to further raise your throughput, that means that each physical partition today can support 10 KRUs. So if your tenant is spread across 2 physical partitions, if you really raise your throughput, you could actually get an effective 20,000 RUs of throughput for that whole tenant, and so on as your partitions increase and as your data size increases. In addition to getting you out of these limits, when you do queries and reads, as long as you give us the exact prefix of the partition key path, it'll go to an efficient subset of the physical partitions. Hierarchical will show a demo of this in a bit. But basically, if I partition by tenant ID, I only go to the either one partition or the very small number of partitions that my data has been split to. If you give me tenant ID and user ID, I can further narrow that down to the one physical partition. And if I had 3 paths here, as long as you give me either like L1, L1, L2, or L1, L2, and L3, it'll always be routed efficiently to the physical partitions.
That's great. So you're always going to be in using hitting a bounded set of partitions rather than unbounded, which is definitely something you want to avoid.
Exactly.
So yeah, that's great. So I know the tenant, but I don't know the user, right? Or I want to run a query that's going to, I don't know, some or do some aggregate on my users. I can do that and still not do a fan out.
Exactly. So you can think of it as like the best of both worlds of partitioning by tenant, as well as the synthetic key and the cardinality you get from doing like a synthetic key kind of partitioning implementation.
Yeah, very cool.
All right. All right. So I also want to touch on two other common scenarios that this feature could apply to. So in addition to the multi-tenant scenario we've already discussed, one other very common scenario is an IoT or device telemetry scenarios. So typically the scenario is you have a very write-heavy workload where you're ingesting a lot of device data into Cosmos DB, but you also have some reads that you want to optimize for. Now, typically for these scenarios, because a device ID can emit a lot of data and quickly hit the 20 GB limit, especially imagine you're pushing data once a second or even once a minute for years, right? Typically, customers today, as a workaround, they'll do the synthetic key of device ID and something higher cardinality like date. But then when you try to query by device ID, it's always cross-partition. So with sub-partitioning or hierarchical partition keys, you can now exactly partition first by device ID and then sub-partition by date kind of natively. So no more synthetic key mucking around that you have to do in your app. Each device ID can now exceed 20 GB of data as long as the total combination of device ID in a single date doesn't exceed 20 GB. And now you don't have to worry about implementing synthetic keys.
That's great. That's a really huge scenario that we obviously see quite a bit as people using Cosmos to ingest high volumes of, say, device telemetry data. And it's always partitioned by date, right? I mean, it's always tagged by date because everybody wants to know, or anybody, like it's useless. Like, when did that event happen in there? So now you've got something that really, I think, really suits that scenario really, really well, in addition to that kind of multi-tenant one you had earlier. So I got a couple of questions. So is this relatable to table API implementation on the first level or third level hierarchy partitions? I don't know. This isn't related to table API at all, as far as I know, right? This is just SQL API today. You guys, this one, you guys, anyone have a comment on that? I don't think, I'm going to say the answer is no. This isn't supported on our table API. This isn't something I would think we could support because it would break the interface for how the table API works from storage. But yeah, if you have a follow-up on that, let us know. And then a comment from Jeremy. This is really helpful. So you've got a fan there already. We'll have a sign up for you folks later if you're interested. I'll put that up a little bit, but not right now. So I want you to stay tuned and see more.
Good to hear. And if you like this IoT scenario, I'll share one more to see if it resonates with any of our other customers. So retail is another big vertical that we see a lot of Cosmos DB adoption in. And this is actually based on some of our customer engagements and support cases we've seen coming in on, hey, I have this scenario. How do I partition optimally for it? So the scenario was you want to store some kind of customer transaction data from, let's say, a retail or physical store in Cosmos DB. And some of your stores might have a lot higher volume than others. And you also may be piloting this in the beginning. You may only have 10 stores you want to try it on, right? Where maybe in the long run, you'll have thousands, but let's say you just start with 7, right? So if you partition by something like store ID on its own, if you only have a few stores and some stores are bigger than others, you're quickly going to run into the 20 GB limit for a store. But if you sub-partition by something with higher granularity, like let's say transaction ID, now each store's data can exceed 20 GB on 20 GB of data, and you can still efficiently do your lookups on store and queries on store, which is typically the query that you want to optimize for. So it doesn't necessarily have to be a store. It could be like a manufacturing site, a factory site, any kind of scenario where you typically want to query by that thing. And then as a second level, there's some other hierarchy natural in that data that you want to query for, or further sub-partition your data. That's a good way to figure out what your next level key should be.
Yeah, I mean, it could be store ID and like say product ID or category or something, right? Anything where you're going to go and run like high volume queries against that. Like how good does this query do in this store, right?
Exactly.
Or I could see it working across anything where you wanted to do maybe more kind of analytics on stuff, where you say you were ingesting stuff, using one partition key to help with kind of smoothing out the writes. But then you wanted to do some kind of light analytics or aggregations downstream. So change feed that into a new container. You can define a new set of hierarchical partition keys that could help serve particular queries, whether it's by sales by some category or state or anything really. And then because you get that hierarchical partitioning, you could serve more queries with it, I guess, is what I'm really thinking, is than you could if you could only do one. So
yeah, the reads definitely get cheaper since compared to fanning out to all partitions, if you can narrow down to one or a subset of physical partitions, if the reads are cheaper, the RUs are cheaper, which means you can either provision less RUs overall, which is great, or for the same RUs, get more performance, right, which is also great too.
Right. Oh, follow up from the first question here. Is this similar to the implementation of partition key and row key, which is used for table API behind the scenes? No, that's not the same. When you have a partition key, I look as a row key as kind of like our ID, and like when you're using key value store, right? If you turn it off, it's kind of the partition key is kind of the building, and the ID or the row key is kind of the unit number for the building. I think is maybe the right way of thinking about that. I don't know. Is that a bad metaphor or analogy? Deb?
Thinking about it. I'll think about it some more and I'll get back to you.
All right, we'll think about it some more, Chetan, and we'll let you know. Okay, cool. What's next?
So I'll turn it over to Srinakil, who's going to show a demo of the feature in action.
Yeah. Thank you, Deborah. And so, let's actually look at a quick demo. And so let's try to mirror the example that Deborah had given us. So where we have, let's compare 3 different containers, one partitioned by a tenant ID, then a synthetic key, and then a hierarchical partitioning key container. So this is a sample document that we are what we usually see. So this is a sample of a payment data. So where someone has like a payment data for some tenant, and this data has a user ID and some transaction ID, right? So today, one famous or one common scenario that we see is being partitioned by tenant ID. So let's see what usually happens when customers do this. So once they create a container, they start ingesting data. And so typically what happens here is now they're trying to insert a document with the partition key Microsoft. Now, let's say this tenant ID has grown large enough that it's exceeding the 20 GB limit for a partition key that we have today. So the next step, or usually the next approach the customer does, is what they do is create a container with a synthetic partition key. So typically the usage here is that they now insert a new field into the document where they create a synthetic key by appending, say, the tenant ID and the user ID value, right? So now typically they start using the synthetic key now as the partition key. So now with using the synthetic key as a partition key and inserting the container works well. So they'll be able to ingest all the data that they want into the container, and it works fine. But as Deborah had mentioned, the issue what they start seeing here is that once they start running queries, now here is a typical example of the queries that we see that's used in the Cosmos today. So they do a select and they specify the tenant ID where it's like, for example, here that's doing a tenant ID equal to Microsoft, right? So in the previous example, in the previous container that they had partitioned by tenant ID, it works well because it's going to only hit one physical partition, and the amount of RUs that they use would be less because it's hitting a targeted partition. But now once they've moved to the more granularity by using the synthetic partition key, they lose out on the locality of the documents and the partitions, and now the query actually hits all the partitions that exist in the container. So they typically end up consuming a larger amount of RUs for the query, right? So this is where the hierarchical partition key helps. So now we can create a hierarchical partitioning key container with using the tenant ID and user ID as the partition key. So what happens is that with the hierarchical partitioning key container, we end up ingesting data that exceeds the 20 GB limit for a single partition. And now, if we already have queries that run using specifying only just the tenant ID as a filter, now you see that typically the RU usage is similar to what we had before, where the data was partitioned with just the tenant ID. And now additionally, we also have the benefit of not hitting the 20 GB limit that we did before.
So why is it a little bit higher if it's still hitting the same number of partitions?
Yes, it is still hitting a single partition. This is probably because I'm looking at the top 1,000 documents here. The size of the documents might vary, and
it's only less than 2 RU difference. That's probably
it's still hitting the right. So currently, like Microsoft exists on single physical partition. So if you observe here, like the hierarchical partitioning key container is partitioned with both the tenant ID and the user ID, but all I'm specifying here is just the tenant ID, but I'm still able to hit the subset of partitions where the data
got it.
exists.
And as Deborah mentioned, this gets worse the bigger you get, right? So
exactly.
So if you see even small changes here, and 30 RU is not a huge difference, but you scale that 10x, it gets progressively worse and worse, right?
Yes. And here I'm limiting the number of documents to 1,000. Say if I have to selecting all the documents, and you see a huge bump in the number of.
Even with the top 1,000, that's still gonna hit every partition and grab everything, right?
Yes, it is. Yes.
That top statement doesn't happen until it's already done all the partitions. So.
That is correct, Mark.
Yeah. All right.
I think it's really cool here to see that if you look at the second row where you compare the synthetic partition key versus just partitioning by tenant, if we estimate about 3 RUs for hitting a physical partition, that RU difference is almost entirely the additional RU cost of hitting the extra physical partitions, right? Which all completely went away once we're able to use subpartitioning to narrow down to the subset of partitions the data will be on.
Right. So it's what you're saying. It's every time it hits another partition, that's going to cost 3 RU just to at least address it first and say, is this range on your partition? And if it's no, then it just moves on. But it's still going to cost you 3 RU to at least go and say hi.
Yep. I think I've heard team members internally refer to it as like the cover charge for running the query.
Yeah, that's a perfect way to explain it. The cover charge. Yeah, that's it. Get behind the velvet rope. Well, this is cool. Very cool.
Yes. Next, we can switch back to the slides and briefly talk about how you can sign up for this and what is available. So today we are currently the feature is still under private preview. So what is supported is today, the support is through the .NET V3 SDK and the Java V4 SDK. And currently, because it is under private preview, you'll have to use the preview versions of the SDK. And currently, this feature is only supported on new containers that you create. And currently, this is only supported for SQL API. We do not yet have support for MongoDB and Cassandra and other APIs that we support.
Can you show me source code? Like what's a read item async look like with specifying a hierarchical partition key or the query? Do I need to add that into my request options as an array of partition keys, or am I using like a where in on my partition key? I'm curious, how do I use this in the
Sure. So typically today we suggest the customers to, if they are using the partition key, to either include it in the query where they can just specify where c.tenantid equal to Microsoft, or today they can use a partition key object as a partition key object to specify the filtering of the query. So in the private preview, currently, like we do not support partially specifying the partition key in the request options. But this is a feature that we are working on, and it's coming up soon.
So in the request options, then the partition key, that's going to become an array. Is that right?
Yes. So today we already.
Go ahead.
Sorry, Mark. Today we already support taking the partition key object as a in the request options. So with the support that is now coming in, we have a newer class named partition key builder, where you can specify multiple partition key values, and that gives you a partition key object. So we've included samples for this already in the subpartitioning docs that we are going to share. But yes, so we'll have to specify whichever partition key values that we want the filters on.
Got it. And then
do you want to show the container creation?
Yeah, that'd be cool to see too.
Sure. So today we support container creation using the container properties object. So now, as of today, we were only supporting a single string value as a partition key path. But now, under this preview, you can now specify a list of partition key paths, where your list could be either 1, 2, or 3 partition key paths that you want to build the hierarchical partition key on. So nothing changes. It's just that now, instead of providing a single partition key before, you now specify a list of partition keys.
Got it. Okay. Yep. That's pretty cool. And then for queries, I don't need to specify. You're still, even if I'm using hierarchical, I can just use them in the where clause, and the query engine will suss out the partitioning within there.
Yeah,
okay.
The query. Yes, Mark. The query routing.
Sorry, that'll work the same than it does today, right? Is what you're saying?
Yes. Yeah.
Okay.
No other change in the specifying the query.
Got it. Okay. Yeah. Very cool. All right. Let me put up your. Oh, I guess Deb, you had some more. Let me put Deb back up in there. Yeah, and I've got your sign up here for the private preview on this SQL API only. Any plans? Is this coming to other APIs in the future, maybe, or don't know yet? Just focused on today.
We're focused on today. That said, there are definitely scenarios where this could be useful for the other APIs. And I think our long-term vision is to bring it to the other APIs where the scenario makes sense. So if you have a specific scenario in mind, let's say on a different API, just feel free to reach out and let us know and see how we can help.
Okay. And then new containers makes sense. You can't migrate an existing container. I get it, because you're talking about where the data, how it gets physically stored in there. So you can't just like push a button and then magically everything is in sub-partitioning mode. So that makes sense. So customers that want to use this, that are building multi-tenant apps or could benefit from this, they'll need to migrate into a new container to do that. Is that right?
They will, yes.
Okay. All right. Cool. Well, is that it for everybody?
Yeah, we're super excited to see your feedback. Please sign up for the private preview. Just give us your account subscription ID. We'll approve you. These SDK versions are already on NuGet and Maven. So once you have your account enrolled in the preview, you can start sending requests against that account, try out the feature. We also have a GitHub repo where we have some documentation and code samples on how to use the feature. So if you have any issues, problems, bugs, just file them as a GitHub issue, and we actively monitor that and we'll respond there.
Right on. Cool. Well, thank you, Deb, for coming back on again. And Srinakil, great having you.
Thank you, Mark.
Let's have you guys back on again. I'd love the the stuff you guys work on around all of the partitioning and everything. It's, I think, one of the more fascinating areas of Cosmos and the elasticity we provide for customers and how that works and how we scale. I mean, you're at the heart of providing scale to customers and their databases. So anyway, come on back on sometime. And folks, if you've got show ideas and you want to say, hey, bring Deb and Srinakil back on to talk about something on throughput or elasticity, just hit us up on Twitter at Azure Cosmos DB and suggest a show idea in there. And then just wrap it up. So, hey, we've got a new Azure Cosmos DB user group. Come and join us. We'll be doing monthly meetups online. You can join there. Just join up on the group, and then you'll get notified when we've got a new user group coming up on there. That's it for this week. Next week, I've got Abhinav is coming back. So Abhinav was on a few weeks ago. And he's going to talk about server-side performance monitoring using the log analytics. So we've been doing a lot of work with the log analytics. We've got these new, very trimmed down new tables in there that are much cheaper, easier to run, and just lots of great new samples in there as well for helping you monitor your applications in Cosmos DB. And for running in a service that's fully managed, being able to get those kinds of metrics and those analytics is super important when you're running production workloads. So come check us out next week and learn more all about that. So that's it for us this week. Thank you, Deb, again, very much for coming on. And Srinakil, thank you, sir, for being here with us.
Thank you so much, Mark. It was a really fun exercise.
Yeah,
great.
Thanks so much, Mark.
You bet. Okay. Thanks, everyone. See you all next week.
Bye.